In this lesson, we are going to learn about polynomials and their characteristics and behaviors. We learn to operate on polynomials and find their characteristics. We learn to use different theorems to find roots of polynomials and factor them and then graph polynomials. Polynomials are functions of this form where values of all a's are real numbers and exponents are natural numbers, and the numbers multiplied by the variables are called coefficients. If you look at a polynomial in standard form, the term with the largest exponent is the leading term, and the exponent of the leading term is the degree of the polynomial. So for the generic form, a sub n x to the n is the leading term, and n is the degree. The leading coefficient is the coefficient of the leading term, and the constant is the term with no x variable, or the term with a degree of 0. So the leading term for the generic form is a sub n, and the constant is a sub 0. Here are two polynomial functions, f of x and g of x. Let's explore addition over polynomials. By definition, f plus g of x means f of x plus g of x. So we simply add the two functions. There is only one x cubed term, so we simply write it down. Then we add x squared terms, x terms, and constant terms together. Subtraction of polynomials is very similar to the addition. By definition, f minus g of x means f of x minus g of x. So we subtract g of x from f of x. Because there is a minus sign outside of parentheses, we need to distribute it into the parentheses before dropping parentheses. Distributing the negative will simply change the signs of the terms of g of x. We then combine the like terms. Let's use the same functions f and g to explore multiplication of polynomials. By definition, fg of x means f of x times g of x. So we want to multiply these two trinomials. We can use the foiling technique, but it gets very complicated since we have three terms in each function. We separate the first trinomial so that each term of the first trinomial is multiplied by the entire second trinomial. We distribute 3x squared into g of x, then distribute 2x into g of x, and then distribute negative 5 into g of x. And finally, we combine like terms. Division over polynomial can be done in several ways. We will explore the long division and synthetic division in this lesson. By definition, f over g of x means f of x divided by g of x. To perform the long division, we use the long division symbol. F of x, the dividend, goes inside the symbol, and g of x, the divisor, goes outside the symbol. Note that we need to make sure we have no skipping terms. Since we have no x term, we use 0x in place of it. We ask, what times 3x squared equals 6x cubed, which is 2x? We write this above the long division symbol, then we multiply 2x by each term of the divisor. So 2x times 3x squared is 6x cubed, and we write it under the like term of the dividend. We then multiply 2x by 0x and write it under the like term of the dividend, and then multiply 2x by negative 1 and write it under the like term of the dividend. Instead of subtracting this from the dividend, like we do in traditional long division, we switch the signs of this expression and then add it to the dividend. Since the degree of the remaining polynomial is not less than the degree of the divisor, we can still continue with the long division. And since the divisor has 3 terms, we need 3 terms to continue with the long division. So we carry down the next term. We ask the question again, what times 3x squared equals negative 9x squared, which is negative 3? We write this above the long division symbol next to the 2x, and then we multiply -3 by the entire divisor. So -3 times 3x squared is -9x squared, -3 times 0x is 0x, and -3 times -1 is 3. Remember, we switch the sign of the expression at this step and then add it to the dividend, and we get 2x minus 1. Note that the degree of the remaining polynomial in this step is less than the degree of the divisor, which means we cannot continue with the long division and we are done. 2x minus 1 is called the remainder of the long division, and 2x minus 3 is called the quotient of the long division. We always express the final answer of a long division as a quotient plus the remainder over the divisor. We have the quotient and the remainder, and we know that the g of x is the divisor. So we express the final answer as 2x minus 3 plus 2x minus 1 over 3x squared minus 1. If we are dividing a polynomial by a linear divisor, we can use the synthetic division. Though there are ways to use synthetic division for other types, I only recommend using synthetic division when the divisor is either x plus a number or x minus a number. The symbol for the synthetic division is different from the long division. The coefficients of the dividend go inside the symbol on the first row. So we write a 6 for the 6x cubed term, a -9 for the -9x squared term, and then a 0 for the 0x term. Remember, there should never be any skipping terms in polynomial division, no matter if it is a long division or synthetic division, and a 2 for the constant term. The polynomial must be in descending order. If not, rewrite the polynomial in descending order before you start setting up the division process. We always carry down the leading coefficient and write it in the third row below the synthetic division symbol. Then we set the divisor equal to 0 and solve for the variable. This number goes outside of the synthetic division symbol to the left of the first row. Again, I only recommend using synthetic division if the divisor is in the form of either x plus a number or x minus a number. We multiply -2 and 6 and write it under -9 in the second row. We then add -9 and -12 and write the value in the third row. Then we multiply -2 and -21 and write it under 0 in the second row, and add 0 and 42 and write the value in the third row. Then we multiply -2 and 42 and write it under 2 in the second row, and add 2 and -84 and write the value in the third row. We set this value aside for now. Going to the left side of the third row from right to left, we give variables to the coefficients. That is, 42 gets no x, -21 gets an x, and 6 gets an x squared. -82 is the remainder, and 6x squared minus 21x plus 42 is the quotient, and x plus 2 is the divisor. So we express the answer of this division as the quotient plus the remainder over the divisor. That is, 6x squared minus 21x plus 42 plus -82 over x plus 2. We can also pull out a negative sign from -82 and express the answer as 6x squared minus 21x plus 42 minus 82 over x plus 2. If we perform a polynomial division and get a remainder of 0, regardless of the division method, then we can say that the polynomial is divisible by the divisor. The remainders theorem says that if we divide a polynomial p of x by a factor x minus c, then the remainder equals p of c. That is, to evaluate a function at x equals c, we can perform the polynomial division by the factor x minus c and take the remainder as the value of p of c. The factor theorem says that if a polynomial is divisible by x minus c, then x minus c is a factor of the polynomial. That is, if the polynomial evaluated at x minus c equals 0, then x minus c is a factor of the polynomial. So putting these together, if p of c equals 0, that is, the remainder of the division is 0, then x minus c is a factor of the polynomial, and c is a root or 0 of the polynomial. If you're able to find roots or zeros, we can factor polynomials. Rational root theorem helps us in finding possible values of c to check to see if there are roots. So, given any polynomial of degree n, when n is greater than or equal to 1, rational roots of the polynomials come from the list of factors of the constant over factors of the leading coefficient. Here is a polynomial in descending order. Factors of the constant term, negative 27, are plus or minus 1, plus or minus 3, plus or minus 9, and plus or minus 27. And factors of the leading coefficient, 2, are plus or minus 1 and plus or minus 2. By rational root theorem, all rational roots come from the list of factors of the constant over factors of the leading coefficient. Plus or minus 1, plus or minus 3, plus or minus 9, and plus or minus 27 divided by plus or minus 1 are plus or minus 1, plus or minus 3, plus or minus 9, and plus or minus 27. And plus or minus 1, plus or minus 3, plus or minus 9, and plus or minus 27 divided by 2 are plus or minus 1 half, plus or minus 3 half, plus or minus 9 half, and plus or minus 27 half. Now that we have a list of possible rational roots, we need to test them to see which of them are actual roots. We can use synthetic division to see which one of these possible roots gives us a remainder of 0. To set up the synthetic division, we copy the coefficients of the polynomial into the first row. Remember to make sure there are no skipping terms. We carry down the leading coefficient, and then choose one of the numbers from the list of possible rational roots, and perform the synthetic division. Unfortunately, the remainder is not a 0 for this number, which means the number we just tried is not a root of this polynomial. So we can cross out 1 as it is not an actual root. We move on to try another number. Let's try negative 1 this time. We set up the synthetic division and go through the process. Since the remainder is 0, the number we tried is a root. So, negative 1 is a root of this polynomial. Instead of using the coefficients of the original polynomial, we use the coefficients of the quotient to set up the synthetic division for the next possible root. A number can be a root more than once. So, since negative 1 was a root already, it may be a root again. Note that to use this technique, we must use the coefficients of the quotient of the division that had a remainder of 0. So let's try negative 1 one more time. Since the remainder is 0, negative 1 is a root of the polynomial 2 times. So since the remainder was a 0, we use the coefficients of the quotient of this division to look for more roots. And since negative 1 worked twice, it may work for a third time. So we're going to perform synthetic division using negative 1 one more time. The remainder is 0 again, so negative 1 is a root of this polynomial 3 times. So we use the coefficients of the quotient to set up the synthetic division to find the next root. And since we had so much luck with negative 1, we're going to use it one more time. The remainder is not 0. I guess negative 1 is a root of this polynomial only 3 times. Since the remainder was not a 0, we go back to the same coefficients as the previous synthetic division, not the coefficients of the quotient, because we had a non-zero remainder. We tried positive 1 and negative 1, so let's try positive 3 this time. Performing synthetic division with positive 3, we get a 0 for the remainder, which means 3 is another root of this polynomial. Since the quotient is a trinomial at this step, we don't need to perform synthetic division anymore to find the rest of the roots. We can solve the quadratic equation by factoring, completing square, or quadratic formula. By factoring the trinomial, we can see that either 2x minus 3 equals 0 or x minus 3 equals 0 gives us x equals 3/2 and 3. So roots of this polynomial are -1 3 times, 3 2 times, and 3/2 once. When we have a root more than once, we use the word multiplicity to describe how many times we have that root. So the roots are -1 with multiplicity of 3, 3 with a multiplicity of 2, and 3/2 with a multiplicity of 1. We can use roots to factor polynomials. Since -1 is a root, x minus -1 is a factor. And since the multiplicity of this root is 3, this factor is raised to the third power. Similarly, x minus 3 is a factor and it is raised to the second power, and x minus 3/2 is another factor. Note that since the multiplicity of 3/2 is 1, it is not raised to any power. Now, if we multiply all these factors, we get x to the 6, whereas the leading term of the polynomial is 2x to the 6. So the factored polynomial we have right now does not equal the original polynomial in expanded form. However, there is an easy fix for it. All we have to do is multiply the factored version by 2. We can simplify the polynomial a little farther to this. So, how are factoring polynomials and knowing multiplicities helpful? Real roots are x-intercepts, and knowing them, we can graph polynomials. For any polynomial p of x, if c is a root with a multiplicity of 1, the graph goes straight through the root, looking like this. If c is a root with an even multiplicity, say 2, 4, 6, or so on, the graph bounces at the root, looking like this. And if c is a root with an odd multiplicity greater than 2, say 3, 5, 7, and on, the graph makes an inflection at that root, looking like this. So for the polynomial p of x that we just factored, since -1 has a multiplicity of 3, the graph makes an inflection at x equals -1, and since 3 has a multiplicity of 2, the graph bounces at x equals 3, and since 3/2 has a multiplicity of 1, the graph goes straight through x equals 3/2. Now that we know how polynomials behave at roots, let's explore the end behavior of polynomials. For a polynomial p of x, if the degree is even and the leading coefficient is positive, the graph goes up on both ends. So as x approaches -infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches positive infinity. If the degree is even and the leading coefficient is negative, the graph goes down on both ends. So as x approaches -infinity, y approaches -infinity, and as x approaches positive infinity, y approaches -infinity. If the degree is odd and the leading coefficient is positive, the graph goes down on the left and up on the right. So as x approaches -infinity, y approaches -infinity, and as x approaches positive infinity, y approaches positive infinity. If the degree is odd and the leading coefficient is negative, the graph goes up on the left and down on the right. So as x approaches -infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches -infinity. So for the polynomial that we just factored, since the degree is even and the leading coefficient is positive, the graph will go up on both ends. And the end behavior is as x approaches -infinity, y approaches infinity, and as x approaches positive infinity, y approaches positive infinity. We already had the behavior at each root. All we need to do is to find the y-intercept so that we can graph the polynomial. This is the easy part, as the y-intercept is the constant term. So putting all this information on the grid, we can graph the polynomial. We know that for the end behavior, the graph goes up on both ends. Then we plot x-intercepts and y-intercepts. Note that real roots are x-intercepts. We know that the graph makes an inflection at -1, and going from left to right, since we approach it from above, it looks like this. and the graph goes straight through at 3/2, and since we approach it from below, it looks like this. And the graph bounces at 3, and since we approach it from above, it looks like this. Connecting these curves, we get the graph of the polynomial. There are other techniques that help us find roots faster. Descartes' rule of signs is one of these techniques to help us identify how many positive or negative real roots a polynomial has. That is, the number of positive real roots of a polynomial p of x is the number of sign changes in p of x or less by a factor of 2, and the number of negative real roots of a polynomial p of x is the number of sign changes in p of negative x or less by a factor of 2. To determine the number of positive real roots of a polynomial, we count the number of sign changes in p of x. We can see that there are 5 sign changes in p of x, so the number of positive real roots is either 5 or 3 or 1. To determine the number of negative real roots of this polynomial, we need to find p of negative x. A negative number raised to an even power becomes positive, and a negative number raised to an odd power remains negative. So we simplify p of negative x to this, and then count the number of sign changes. Since there are no sign changes in p of negative x, there are no negative real roots. This polynomial has a degree of 7, so it must have a total of 7 roots. We identified that there are no negative real roots, and there may be 5 or 3 or 1 positive real root. And so there is at least 2 complex roots. Complex conjugate root theorem says that for a polynomial with real coefficients, if a plus bi is a root, then its conjugate, a minus bi, is another root. And irrational conjugate root theorem says that for a polynomial with rational coefficients, if a plus square root of b is a root, then its conjugate, a minus the square root of b, is another root. Here's an example where we are asked to find all real and complex roots of p of x, given that 2 minus I is a root of this polynomial. We can see that all coefficients of this polynomial are real numbers. But complex conjugate root theorem, since 2 minus I is a root, 2 plus I is another root. We also know that x minus a root is a factor of this polynomial. So x minus the quantity of 2 minus I and x minus the quantity of 2 plus I are factors of p of x, meaning that the polynomial is divisible by each of these factors. Since the polynomial is divisible by each of these factors, the polynomial is also divisible by the product of these factors. Going through the process of multiplying these factors, we get these terms. We can see that negative ix and positive ix terms cancel each other out. 2i and negative 2i terms cancel each other out. And we also know that I squared equals negative 1. And so negative I squared would equal positive 1. And the product simplifies to x squared minus 4x plus 5. Note that the product of two factors with imaginary roots gives us a quadratic factor with real coefficients. So the polynomial divisible by each of the factors is also divisible by x squared minus 4x plus 5. If we divide the polynomial p of x by this factor, x squared minus 4x plus 5, using long division, we get a remainder of 0. And the polynomial can be factored to the product of the divisor and the quotient. That is, p of x equals x squared minus 4x plus 5 times x squared minus 2x plus 2. So far, we know that the polynomial factors to x minus 2 plus I times x minus 2 minus I times x squared minus 2x plus 2. Remember, we are asked to find all real and complex roots. We were able to find complex roots using complex conjugate root theorem. We performed the long division to find the rest of the factors, and since the remaining factor is quadratic, we can use quadratic formula to solve the equation x squared minus 2x plus 2 equals 0, and simplifying it, we can see that 1 minus I and 1 plus I are two other complex roots. So the roots are 2 minus I, 2 plus I, 1 minus I, and 1 plus I.